Hello, everyone. Here we are in day 9, and we're moving on to the second topic of the day. Sorry, let me adjust my camera here. Uh, so we talked, there's kind of two big orders of business today. We talked about sovereign debt crisis on day 9. And then we also want to talk about a little bit of review for some of you, or introduction to econometric or regression analysis. Right, so this is really to help prepare you for homework number 3. Remember that Money and Banking is a quantitative reasoning course in the ECB major. And so one of the things that we've been trying to develop here in your first 2 homework assignments is to try to develop your abilities and your skills in analyzing data and improving your ability to reason using quantitative data. And so homework number 3 deals specifically with taking data, putting it in a form in which you can do regression analysis. And so I'll talk a little bit about homework number 3 here at the end of this section of lecture. But before we do that, I wanted to just kind of give you a brief introduction into what do we mean by regression analysis, or I'll often refer to it as econometrics, which is the application of regression analysis to economic problems. Right? So, what can you learn here about some of the basics of econometrics? Right? Okay, so let's go to our notes. Oops. There we are. Okay, so here's our introduction to econometrics. Econometrics really is just the application of statistical methods to economics. And so let's talk about a basic econometric or regression model. And it usually takes the following form. Now, before you get freaked out, those of you who are a little leery of math, right? This is actually just a mathematical representation of a pretty simple idea, right? The idea here is that one variable is caused by another variable, okay? We call YT here the dependent variable, right? I should have written this up here in our notes, but the dependent variable, meaning this is the variable that we're interested in exploring. Sorry about I don't know if you can hear the noise in the background. Someone is obviously doing some track and field practice in my house. So, so YT is the dependent variable, or the variable that we're trying to explain. And XT is the independent variable, or the explanatory variable. So what we say here in this setup is that these X's, these are variables that cause Y, right? What is the betas here then? The betas are what we call the coefficient, or the impact of each of these X's on Y. So beta 1 captures the impact of X1 on Y. Beta 2 captures the impact of X2 on Y. Then we have an intercept, or a constant, right? And so this is just an additional fixed impact of X on Y. And then finally, we have U, which is the error, recognizing the fact that no model is going to be perfect. We're never going to be able to explain everything that goes on with our dependent variable, but we can explain some of it. And so this is how an econometric model is set up, where we have explanatory variables and our dependent variable. And we're saying that these explanatory variables cause changes in Y, our dependent variable. Notice here that I also have little t's to denote that this is time series data. In other words, this is data measured across time. So to get an example, let's say in homework number 2, you picked consumer borrowing as the financial variable that you're interested in exploring, right? So Y here is going to be consumer borrowing. That is the dependent variable. That is the variable that you're interested in explaining. What would then be some of the explanatory variables that you might want to consider? Well, you might say that maybe consumer borrowing is influenced by consumption patterns, or what people's income is, or what interest rates are, or what unemployment are, or other things, right? We won't even talk about what these other things are, right? Then we would expect that there would be some sort of relationship. This should not be interest rates. I'm sorry about this. So when I made this, right? That should be income, right? So let's say that we picked a relationship between what is the relationship between consumer lending and income here. And what we might find is that when income goes up, consumer lending goes up. And these little blue dots are just essentially plotting our data. For every data point, for every period that we have data, we can see what income is and we can see what consumer lending is. What is regression analysis? Regression analysis is essentially fitting a line that best fits the data, right? And by fitting a line, what we mean is we're trying to determine the best betas and the best alpha, right? In other words, the best intercept and the best slope of this line that fits the data the best, right? Once we know that intercept and that slope, then we can say something about how X impacts Y, right? So in this case, how income impacts consumer lending. So how do we do that, right? How do we get the best estimates of alpha and beta? And we, in regression analysis, we call these estimates alpha hat and beta hat. The hat here denotes that they're estimates of alpha and beta because we never know the true, quote unquote, true alpha and beta, right? We never know the true intercept and the true coefficient. We just can obtain estimates. And that's what regression analysis is. Regression analysis is figuring out what the estimated relationship between X and Y is. The most common method of obtaining estimates for alpha hat and beta hat is what's called ordinary least squares, or OLS. Ordinary least squares is a technique that essentially chooses alpha hat and beta hat to minimize the sum of squared errors, right? So if we go back to this equation, right, what is ordinary least squares doing? It's picking different alphas and different betas, trying to find out the combination that minimizes the sum of squared errors, right? So that's our error, our estimated error, squared for every observation and summarized across all observations that we have, right? Another way that you can see this error is the error is the difference between our dependent variable and then our estimate of the dependent variable, right? So in other words, what's our estimate based on our alpha hat and beta hat? We figure that out and we compare it to what Y actually was. That difference is the error. We square that, right? Oh shoot, keep on finding mistakes here. This should be squared, right? So sorry about that. But this whole thing should be squared. And then we summarize it over all observations. In other words, what ordinary least squares is trying to do is it's trying to find a straight line that best fits the data. Now, just to understand why ordinary least squares behaves like this, you might ask, why do we take the sum of all data? Well, I think that's pretty obvious, right? We want to do the sum because we want to use all information available. We don't want to do this just for one or two observations. We want to do this for all observations. Maybe the trickier question is, why squared, right? Why are we using squared errors instead of just, why couldn't we just have a technique that just minimizes the sum of all errors? And so by squaring the errors, ordinary least squared is trying to do two things. First off, it's trying to magnify large deviations and weighs them more heavily. So ordinary least squares essentially tries to minimize big mistakes. It's much more likely to accept a lot of little mistakes as opposed to one or two big mistakes. And that's something that's very important to note about ordinary least squares, is that one or two observations that are way off can really change your results, right? That's what we call an outlier. And so one of the things you might want to do when you look at your data is look and see, are there outliers here, right? Are there unusual things in which one or two observations might really be impacting your data? The other reason why we square errors is because it makes all errors positive. if we just added up the errors, the negative errors would cancel out the positive errors, and it might make our model look like we're explaining more than we are. And we don't want to do that. So by squaring the errors, not only are we putting more weight on big errors, but we're making all the errors positive, right? And so that way we can make sure that we incorporate all the information and just don't let some of that information cancel itself out. How exactly do we do this? How do we minimize the sum of squared errors? Well, first off, this is a calculus problem, right? Minimizing a function is a calculus problem, but in practice, this is why we have computers, right? Computers essentially allow us to do this quickly and relatively painlessly. In fact, in many ways, while computers allow us to do this very quickly and painlessly, there's a problem. And one of the problems is it's so easy to do this on a computer. And I think you'll see that when you do homework number 3. It's so easy to do it that oftentimes people will just conduct regression analysis, get some results and say, there you go, and not really understand what they're doing, right? And so that's kind of the purpose of our lecture today, is to kind of at least have some beginning idea about what we are doing when we do regression analysis. And so let's talk about that here. Does ordinary least squares always work best, right? When can we say that ordinary least squares regression analysis gives us good results? In general, our estimates of alpha and beta, we call alpha and beta hat once again, are blue, meaning they're the best linear unbiased estimators, if they have 2 properties. One is that they're unbiased, and unbiased means that on average they're right? It doesn't mean that there's not mistakes in our estimates, right? Sometimes they could be too high or too low, but they're not predictably wrong, right? On average, they are right. That's essentially what unbiased means. In some sense, it's closely related to the idea of rational expectations, right? When we talked about when your expectations of the future are not predictably wrong, right, then your expectations are rational. Well, another way of saying this is that rational expectation says that people are unbiased. They form unbiased expectations of the future, right? They don't consistently miss one way or another. Also, ordinary least squares is best when our estimators are efficient, meaning the variance is as small as possible. So in other words, when we make mistakes, our mistakes aren't huge, they're small, right? We want to have smaller mistakes. And so there's not nearly as much variance around our estimates, right? So if we have an estimator that has a huge variance, that's not going to be a very good estimator, because it means that if we're wrong, we could be wrong by a ton. Now, how do we know that ordinary least squares estimators are blue? Well, we only know this if they fit some conditions, and we're not going to get into the details of what these conditions are. That, quite honestly, is the purpose of taking an econometrics class from me, or a statistical regression analysis class in the stats department, right? Where you'll talk about much more the detailed conditions needed to have blue estimators. But for our purposes, I want to talk about 3 things that often happen in economic and finance data that prevent our estimators from being blue, right? In other words, 3 problems that often exist in financial data that you should be aware of and you should be looking for. The first problem here is simultaneity bias, right? Right. In our model, we assume that X causes Y, but what happens if Y also causes X, right? So in other words, maybe the causation moves both ways, right? All the way back here, we talked about this model where Y is consumer borrowing and X is income. So does income impact consumer lending? Yes. But could it also be true that consumer lending impacts income? Yes. And so almost inevitably, there's going to be simultaneity bias in this model. And that could give us biased results. We could get biased results. Here's just a couple of other examples, not necessarily from finance, but from economics, about where you might get simultaneity bias. What happens if you estimate how education impacts economic growth? Well, does education impact economic growth? Yes. Does economic growth impact the amount of education people get? Yes, right? Or how about guns and crime? Do more guns lead to less crime or more crime? Well, it's really hard to say because having more guns might impact the amount of crime, but then the amount of crime might impact how many guns people own, right? The basic problem here is that ordinary least squares can't separate the impact of X on Y and Y on X. So there are ways to correct for this, and those ways are beyond the scope of our lecture today. But I'll just say that you should be aware of simultaneity bias. And if you see it, you need to make sure that you are at least aware that this could be impacting your results. And if you're actually doing research, you have to figure out ways that you can control for this, right? But that would be a higher level than what I'm expecting you to do on your homework. So in other words, in your homework, I would expect you to be able to recognize simultaneity bias, but I'm not going to ask you to do anything about it. Here's another potential problem that will lead to ordinary least squares not giving us very good estimates. And that is if you estimate your model, but you don't account for trends in the data, right? If you use time series data, which all of you are going to be using, meaning data over time, but you don't think about trend, right? If X and Y have trends in it, then ordinary least squares makes the correlation look much stronger than it should, right? And so this is a common mistake that people make. If X has a trend and it's going up, and Y has a trend and it's going up, it's going to make the variables look much more highly related than they are, right? And this is an example that's common in, or you can be common in finance, but really in any sort of data, is people will look at data and say, oh, look, that one's going up, that one's going up. They must be related, right? But in fact, they might have nothing to do with each other, right? They just might be examples of what we call spurious correlation. So I gave you one of the handouts I gave you here, if I can find it, is on spurious correlation. Here it is. So there's this website that has basically found all these crazy examples of spurious correlation. And if you look at these examples, you'll see almost inevitably it's because you have two variables that have similar trends, but they have they can't have anything to do with each other. So look at this one. One is US spending on science, space, and technology. The second is suicides by hanging, strangulation, and suffocation. Right? Notice that they both have a positive trend that's very similar. If I did a regression model, it's going to look like suicides cause more spending on science. But of course, that's ridiculous, right? The problem is we haven't detrended this data. And so by not taking the trend out, it makes these look much more related than they are. You can flip through this handout and see all of the kind of crazy, crazy relationships they found, like divorce in Maine relative to per capita consumption of margarine, the age of Miss America versus murders by steam, hot vapors, and hot objects, right? Per capita consumption of mozzarella cheese versus civil engineering doctorates, right? People who drowned after falling out of a fishing boat versus the marriage rate in Kentucky, right? You know, it keeps on going on and on. The basics here is that you got to think about trend and controlling for trend, right? And you got to try to take the trend out. And then the other theme is you have to just think about, does my data make sense, right? You have to use intuition, right? Anytime that you just try to look for correlations and you don't think about, does this actually make sense? You're just doing bad research, right? You got to use your brain. You just can't use a computer to chug out numbers and tell you what you're supposed to be thinking. So what happens if you do have time series data with trend? Well, you have to detrend the data. And here, once again, to detrend the data, how do you do that? Gets a little bit beyond what I'm expecting you to do in this class. But one simple way of detrending data, or coming close to detrending data, is instead of using your model with X and Y, why don't you use the change in X and the change in Y? So in other words, don't look at what what the variable is each period, change your data so that it's looking at the change in the variable each period, and then use that in your model. And you likely will find that you get much different results if your data has trends in it. The third thing that can ruin your results is having omitted variables, right? What if there's important explanatory variables that you don't include in your model? That's going to bias your coefficients. It's going to bias your results. You have to have all of the important explanatory variables included in your model, right? So economists are always asking, do you have the right model, right? And by that, oftentimes they mean, do you have the right explanatory variables in there? If you don't, then you can't believe your results, right? So example that I saw in the news recently, there was a study that found that kids who eat more hot dogs have higher instances of childhood cancers. And I think the conclusion that article was trying to get you to believe is that eating hot dogs causes cancer. Of course, I can't believe that at all, right? Why? Because there's tons of omitted variables there that might be, might be the real cause for what this relationship is. So for instance, what's true about kids who eat more hot dogs? They're probably poor, right? They might be living under power lines. They might be more exposed to other carcinogens. They might eat poor quality foods in general. They might get less health care. We could go on and on, right? There's probably omitted variables. There's things that hot dogs are related to that might actually be causing the cancer. So it's not the hot dogs that are causing the cancer. It's other omitted variables that are causing the cancer, right? And so just to say, well, hot dogs cause cancer, no, that's just bad analysis, right? And so you have to ask yourself, am I controlling for other important variables? Meaning, do I have the right X's? And so this is also something I'm going to ask you to think about in your homework is, do you think you have all the explanatory variables, or are there other ones that you're missing? All right, that's the first part of our econometrics lecture. I want to just do a second quick part here, talking a little bit about hypothesis testing, and I'll say a word or two about homework number 3. Okay, back in a moment.